Can you hear me?
Yes, sir.
Yes, sir.
Okay, so let us begin. We are discussing about radiation from accelerated point charge, and today I will discuss a couple of application of those formula which you have learned. The screen is the screen visible to all of you?
Yes, sir.
Sir.
Okay. Okay. So let us begin from the formula, the Larmor formula, which is applicable for a non-relativistic point charge. I will discuss a couple of examples or kind of problems that you are expected to solve. So we are, let's start. Radiation from accelerated point charge, and we shall start with non-relativistic case. So the non-relativistic case is a case when beta is much less than 1. Beta is much less than 1. So this the one of the very simple example of the application of Larmor formula, which is, what is the Larmor formula? If you remember, the power radiated by an accelerated point charge moving with non-relativistic velocity is given by, this is the Larmor formula, P equal to 1 over 4 pi epsilon 0, then twice q square a square by thrice c cube. A is the acceleration of the point charge and q is the magnitude of the charge, and this formula is known as Larmor radiation formula. Now, given any problem, I mean, you see this formula is quite simple. It just depends on acceleration and the magnitude of the charge. So in any problem, you have to just calculate the acceleration, the magnitude of the acceleration, and then just use that in this given formula to calculate the power, amount of power radiated by the point charge. So it could be an electron, it could be some other charge, and depending on the energy of the particle, it can have different acceleration, and given the acceleration and the magnitude of the charge, you can have a different amount of power. So let us first discuss the one of the very important application of this formula in case of, say, all of you probably know the Rutherford model or atom model. I mean, this is something which is discussed in, I think, in school textbook. The Rutherford model, all of you know that there are some defect of this model which is often discussed in those books, that in classical physics and classical electrodynamics, you do not expect this model to be hold. I mean, because in Rutherford model, what we assume is that the positive charges inside an atom are confined in a small region called nucleus. That is the case for all other models like Bohr model. But in this Rutherford model, you have a positive nucleon, and surrounding it there are circular orbits, right, around which the charged particles are, or electrons are basically, uh, they are moving in a circular path. So electrons are moving in a circular path. So there was no concept of quantized orbit at that time. So when Rutherford proposed this model, this idea of quantized orbit were not there. So if you consider an electron moving in a circular orbit, and we already know that any charged particle or any particle which is moving in a circular path has some non-zero acceleration, because the direction is changing all the time, because velocity is along the tangent this circular path, and acceleration is towards the center. So they are orthogonal, and this acceleration is changing all the time. And suppose let us take a hydrogen atom, simple one. So there is a proton, so it's a proton. So this is a electron, and let's call it the proton. Some plus, plus same amount of charge but opposite. And suppose this is the first orbit, so let us call the radius is r. And how do we prove that this is not possible? I mean, if we do not have any quantized orbit, and we just consider an arbitrary radius r where this electron is moving along a circular path, this orbit will not be a stable orbit. So that can be easily shown from this formula. Why? Because you can simply calculate the acceleration of this electron, and use that in this problem. So when we have a stable circular orbit like this, we know so I mean this electron and proton, they are bound together by this electrostatic Coulombian force, which can be simply given by E square divided by 4 pi epsilon 0 r square. This is the force, which is balanced by the centrifugal force, which is mv square by r, where m is the mass of the electron, mv square by r is the radius of the orbit, right? And from this you can simply write v square by r, which is nothing but the acceleration. This is acceleration a, v square by r, which is e square divided by 4 pi epsilon 0 m into r square. So this is the acceleration of the electron in the circular orbit. And once you know the acceleration, you can use this expression for acceleration into this formula to calculate the power radiated by the electron. So let us calculate that. So total power radiated by the electron is given by, okay, I can simplify this simply, q square a square, if I don't write this, 224, so 326, 6 pi epsilon 0 c cube equal to q square by 6 pi epsilon 0 c cube, and a square, a is v to the power 4 by r square, or you can just straight away put this v square by r, which is, this is acceleration. So this is simply e square divided by 4 pi epsilon 0. This is mass of electron, you can write me if you like, me, mass of electron, me into r square to the whole square, the square of that. And I mean, in case of hydrogen atom, we know the radius of the first Bohr orbit, which is r equal to 0.53 angstrom. So let us take the first orbit. This is the radius, and of course the charge of electron is known to us, which is 1.6 into 10 power minus 19 coulomb, and mass of electron is given by 9.1 into 10 power minus 31 kg. Epsilon 0 value is a constant, 8.85 into 10 to the power minus 12 farad per meter. And if you plug in these numbers in this formula, you will end up with this value. What is that? So pt will be approximately of the order of 3 into 10 to the power 11 electron volt per second. This is the power radiated by the electron in the first orbit. This is the prediction of the Larmor formula. So any particle, point charge, which had some acceleration within such a circular orbit of radius 0.53 angstrom, having this kind of charge and mass, should give rise to this kind of power. It should radiate such power. Now you remember what is the energy of this first orbit from we already know the first orbit in the hydrogen atom. Electron has energy how much? This first orbit, this is given by 13.6 electron volt, right? This is the energy. And what is the power radiated per second? This electron radiates 3 into 10 power 11 electron volts. So naturally you can see that within a very very short time. So if I calculate how much time it will require to dissipate all the energy, so the time taken by the electron to dissipate all the energy of this orbit is given by 13.6 divided by 3 into 10 to the power 11 electron volt per second, which will be of the order of 4.3 into 10 to the power minus 11 second. So you can see, so this is a very short time, 10 power minus 11 second. So within a very short span of time, this electron will move from this circular orbit and it dissipate. I mean, as soon as it dissipates all the energy, it will no longer be in bound orbit anymore. So this orbit will not be a stable one. So that was the defect. This is basically a defect. This is a defect of Rutherford's model, and that's why when Bohr proposed his model, he has to introduce some kind of this stationary orbit, idea of stationary orbit, where the charged particles cannot give, they cannot radiate energy, right? So that's something that's come into the area of quantum mechanics. I'm not going into that, but from the idea of classical electrodynamics, any charged particle moving in a circular orbit should give rise to electromagnetic radiation, and the power radiated should be calculated by using the Larmor formula in case of non-relativistic motion. So this is the defect of Rutherford model. So this is one application of Larmor formula. But I think you can apply this formula anywhere, wherever you have some charged particle moving with non-relativistic velocity. You can calculate the amount of power radiated by the point charge. So let us discuss a couple of other example. Some of these examples are from textbook. Okay, so I'm discussing just a couple of examples to give you an idea. Suppose the second application that I am discussing here. Suppose there is an electron which is deaccelerated at a constant rate. So that deacceleration is given by, say, A. A can be called acceleration or deacceleration. In this case, suppose the electron is deaccelerated at a constant rate A from some initial velocity v0 down to 0. So the initial velocity is v0, and then it's deaccelerating, and finally it reaches 0. And this is the deacceleration, constant deacceleration. Right. The question is what fraction of its initial energy. So when it's a velocity v0, of course you can see that it is some kinetic energy, right, which can be calculated, or the total energy. You can, if it is relativistic, then of course you have to use the relativistic formula. But it is non-relativistic, you can simply use the non-relativistic energy. So the kinetic energy of the particle is given by simply half of m v0 square, right? And the particle is deaccelerating. Now whether it's accelerating or deaccelerating doesn't matter. Whether if there is an acceleration, positive or negative, you will expect some radiation from that point charge. In this case, of course, it is given that v0 is much less than c, right? So another important thing I should mention here, that when a charged particle is radiating energy, where does it get that energy from? So it is not creating new energy. So that particle which is moving either under some mechanical force or in some electric field or some magnetic field, whatever. So you are pumping energy in the field, and that energy is actually taken by the point charge, and it is just acting like an outlet from which this energy comes out. So this point charge is basically acting like an outlet of energy, but it has energy source, which is either the electric field, magnetic field, or the mechanical force that you are applying to the point charge. and that once that energy leaks out from the field. So basically so in this case particular case, we just have a particle moving with some velocity v, so it is some kinetic energy, and when it radiates, this kinetic energy will decrease, right? Definitely it will decrease. So it will lose a certain amount of energy in the process of radiation, right? And here the question is what fraction of its initial kinetic energy. So v0 is the initial velocity, finally the final velocity is 0, so there is no kinetic energy in some sense, but what fraction of its initial kinetic energy is lost to radiation. Of course, if it is deaccelerating, of course its velocity is decreasing, but not all of its energy is going to radiation, right? So what fraction of energy, its initial kinetic energy, is lost to radiation? That is the question, right? So that's very again straightforward to calculate, because you know this Larmor formula. What is that formula? This is 1 over 4 pi epsilon 0, and then twice q square a square by 3c cube. If it is in electron, I just put e here, and I just have to calculate the acceleration. Now you just apply the concepts that you have learned in your school, so that it's the final velocity is 0, initial velocity is v0. So what is the time taken from going from v0 to 0? Because we know the acceleration, so v equal to u minus ft, the acceleration u is what? U is v0 here, u is v0, and minus f is acceleration is a, and t, this is for the negative acceleration, that's why I put a minus sign here. So this is the final velocity, initial velocity minus acceleration times t. So this gives us t equal to v0 by a. And why do we require this time? Because if you want to calculate the total energy lost, can be only obtained if I have the amount of time over which the particle radiated the energy, right? So this is the time taken by the point charge for moving from this initial velocity v0 down to this velocity of 0, that is it's coming to rest. So what is the time? And then you can simply calculate that amount of energy radiated. So all that you need to do, you just have to multiply. So E energy radiated, energy lost or energy radiated is this power, the formula, this is the energy radiated per second, and this is the time. So pt cross t into t, that is this one. So you just have to write down this 1 over 4 pi epsilon 0 twice q square a square by 3c cube, and then multiply with this v0 by a. Again, see what are the given quantity. You have to remember what are the given. So your final expression should come in terms of the given quantities. So what are the given things? You know, we because the things that are given is v0 is given, and acceleration is also given, right? So and the question asks that what fraction of initial kinetic energy. So this is the amount of energy radiated, and this was the initial kinetic energy. So you are asked to calculate E radiated divided by E initial kinetic energy. Okay, Ek initial, you can say also Ek initial. So now you have both the expression. This is the total energy radiated, but again you can, if you want, you can write down this a in terms of v and d, the distance. So suppose the distance traversed by the particle is d, suppose it is given, then you can also write down the acceleration in terms of d by using this formula, where okay, let us first write down this one and then we can substitute that. So this will be simply q square, you can cancel this one, q square a v0 divided by 6 pi epsilon 0 c cube into half mv square, that is 2 by mv0 square, and if you want to put a in terms of this distance d, you can write again in this using the same formula. This will be v square equal to u square minus 2 into f into distance traversed. So you can use 0 equal to v0 square minus 2 times acceleration times the distance d, which gives you acceleration equal to v0 square by simply 2d. You can substitute this in place of a to simplify this further, right? right? A one A is cancelled, right? This is a square, this is a, so that's why we have a, only a here, not a square. So you can put just this expression in terms of v. I'm not writing that. You can just put v0 square. So v0 square will be cancelled out, and then the entire the final expression will come in terms of only v0 and d. Q square v0, this v0 square, this v0 square will get cancelled, I think, yeah, and then 6 pi epsilon 0 m cq times d, right? Uh, uh, Next, let us consider another example where we have a capacitor. We have a capacitor, and suppose an electron. Suppose this is positive, this is negative. So an electron going from, say, to this, the plates of the capacitor are at a distance, say, d, and the electron goes from, say, so electron is initially at rest, say v equal to 0, velocity is 0, charge is, say, or it could be any other particle q, and say mass is m, and the particle gets accelerated by this positive, attracted by this positive plate, and gets accelerated. So it goes from here to here, and in this path, what is the amount of radiation emitted by the charged particle? So you can again calculate. I mean, all these problems are similar. The only thing that you have to calculate is the acceleration. Given the problem, these are non-relativistic case, so only you have to deal with the Larmor formula. So you have this p equal to 1 over 4 pi epsilon 0 2/3 q square a square by c cube. Again, in this example, since we have to how to calculate the acceleration, the initial velocity is 0, v is 0, right? And it's a capacitor, so there is electric field, right? Electric field. So how what is the given? Electric field E is given by voltage applied by distance, E equal to v by d. And what will be the acceleration of the electron or the point charge? A will be given by the force acting upon it divided by the mass of that point charge. It could be electron, it could be some other charge. And what is the force in this case? See, there is an electric field E. The force will be simply Q times E. Q times E. This is the force. And if you want to replace E with the applied voltage, you can write Q times V by m into d. E is v by d. So this is the acceleration in this. So we have to use this expression of A in this formula, and we also need to know the time taken by the point charge to come from here to here. Right? Again, it's the same thing. I mean, we already have seen that how to calculate that. So in this case, since the distance traversed will be, see, in the previous case it was deceleration. Initial velocity was v0. The charge was getting slower and slower because of the deceleration, and finally it is coming to rest. But in this case, the initial velocity is 0, the charge particle is accelerating. So in both the cases we have radiation, but you have to calculate the time according to whether the particle is which formula should we use, that you have to decide. So in this case, time t will be given by, so d will be 0 plus half of a into t square. So this gives you the time taken by the charged particle to go from one plate to the other plate is 2 times d by a. And you already know what is a, right? A is already this is a calculated, right? So the total power radiated by the point charge during this interval, during this going from one plate to other, is given by the energy radiated. E radiated will be the power. The power, this is, say, pt power time the into time taken by the charge to go from one plate to the other. So again, this is simplified, 4 pi epsilon 0 twice q square a square by 3c cube into root over of 2d by a. I'm not simplifying it. You can simplify it because all the expressions are known. You can adjust the powers of different quantities of a, d, because a can be written in terms of q, v, m, and d. So suppose the numerical values are given. Suppose I have applied 20 volt, and suppose the particle is electron. The mass and charges are known to you. So how much, and suppose this d is 10 centimeter. So how much power will be radiated by the point charge? That you can calculate numerically. So I'm not simplifying this because this is all algebraic. Just have to simplify the powers of different this D, A, V, and so on. So I just gave a couple of example, because one can formulate different kind of problem, and based on the situation you just have to calculate the acceleration, and based on the question, if the question asks what is the total energy radiated, then you have to also calculate the time over which the particle is radiating. If it is only asking you to calculate power radiated, then you just have to apply the formula for power, which you did for this Rutherford model. So these are the non-relativistic cases where we applied Larmor formula. Next, let us come to the Leonard formula, because there are two formula, each meant for each meant for different region. One is for non-relativistic regime, another is for relativistic regime. So I shall also discuss a couple of example of relativistic motion. We have already discussed about the Leonard formula and the radiation pattern that we expect in case of relativistic motion, specifically when the velocity and acceleration are collinear, or the velocity and acceleration are orthogonal to each other. So you may have heard about this name, cyclotron radiation, cyclotron, or cyclotron radiation. Cyclotron, what is cyclotron radiation? This is a name which is given to the radiation which is coming out of a point charge which is moving in a circular path with non-relativistic velocity. The other one is synchrotron radiation, right? Synchrotron radiation. Synchrotron radiation. Synchrotron radiation. So in cyclotron radiation, gamma is of the order of 1, it's non-relativistic, right? Whereas synchrotron radiation, gamma is much greater than 1, right? This is the non-relativistic case, synchrotron radiation. So an electron, suppose there is a magnetic field, so it can be anything, electric field, magnetic. Suppose there is a magnetic field B, and a charged particle is gyrating around this magnetic field in circular path. It could be a helix or a circular path, and based on the amplitude of the magnetic field, the particle can have different acceleration. It also depends on the magnitude of the charge and the mass of the particle. So it will produce some radiation, and we have already learned about the radiation pattern. If you remember, when a particle moves in a circular path, I'm drawing the this view where this is the charge. Suppose this is the charge particle which is moving in a circular path. We have seen in the so this is the direction of velocity beta, and this is the direction of acceleration, right? This is the direction of acceleration beta dot, right? They are orthogonal, and the radiation pattern we have seen, this is proportional to cos square theta, where theta is the angle between the radius vector curly r and the velocity vector beta. So the radiation pattern goes like cos square theta. So you have a pattern like this radiation. We have a radiation going to forward direction and backward direction. There are no radiation in any other direction. And so this is the case of say cyclotron radiation. In case of synchrotron radiation, the picture changes a little bit, but again you have to apply the Leonard formula. In this case it's Larval formula, in this case it's Larmor formula. In this second case, cyclotron radiation, again this is the direction of velocity, this is the direction of acceleration. The point charge is moving in a circular path, suppose it is moving like this. So the radiation pattern will look like this. We have discussed about this front lobe will be longer and the backward lobe will be shorter in case of relativistic motion. And as you increase the velocity, this forward lobe will be longer and longer, finally tending towards infinity. The length of the forward lobe will tend to infinity, while the backward lobe will shrink to almost like to a point in the limit beta tends to 1. So this is the difference between the radiation pattern. And this should be here we should use Leonard formula, here we should use Larmor formula, and these two names given to radiation coming from the point charge. You see that it is the same, the path is circular, the particle is electron, only difference is the magnitude of the velocity. In one case we call it cyclotron radiation, another case we call it synchrotron radiation. So you should be clear about that. Okay, let us discuss one by one. So if a charged particle, say an electron or anything, is moving in a circular path, earlier when we discussed about Rutherford model, there we have the electrostatic force between the nucleus of the proton and the electron. Suppose in this case we have a magnetic field. Okay, with magnetic field, and suppose this around this magnetic field a charged particle is moving along a circular path. In this case, the force, the force acting is the Lorentz force, right? There is no electric field here, only magnetic field. So Q V cross B, and V and B are say, orthogonal. So the force acting is a Q V V, which is balanced by this centripetal force mv square by r. So the acceleration a is simply v square by r, which is q v b by m, right? This is a very familiar motion. We have, I think you have learned earlier. There is a frequency called Larmor frequency, because this can be also written like mv omega equal to qvb. So omega equal to qb by m is the frequency of gyration, which is called the Larmor frequency. Larmor frequency. This is very important frequency in plasma physics, but I don't know whether we will be able to discuss those things in this course or not. So let us just calculate straight away the power radiated by an electron or charged particle moving in a circular path around a magnetic field, a constant magnetic field. So since it is non-relativistic, we can straight away use this Larmor formula, which we discussed earlier. So 1 by 4 pi epsilon 0 twice q square a square by 3c cube. What is a here? A is v square by r, which is q square v square b square by m square. So we can write 1 over 4 pi epsilon 0 twice q square by 3c square c cube into q square b square b square by m square. You can simplify it a little bit. You can if you want, you can write this in terms of beta. 1 by 4 pi epsilon 0 twice q square q to the power 4 beta square b square. What is there? I think I have taken a c from here, so that c square, so there is only one c left, so 3 m square times c. So this is the power radiated by a point charge moving around a constant magnetic field B. So you can see what are the quantities which decides the amount of charge to be radiated. So of course, if the mass of the particle is large, the amount of radiation that you expect will be smaller, right? Also, if the charge is higher, this depends q to the power 4. You can clearly see this is sensitive, very sensitive to the magnitude of the charge, right? If you take a charge which has a higher charge, so that the point charge which has a higher charge, the amount of power radiated by the charged particle will be higher. And it also depends on the amplitude of the magnetic field. It's proportional to b square, right? So by just simply increasing the magnetic field, you can have a situation where the charged particle will lose more power. But anyway, see, losing power is not very good, because when we design, say, an accelerator, we want to accelerate those particles to very high energy, right? Very high energy. So why should we be interested in losing power? A charged particle will always lose power. But again, if our aim is to accelerate them to very high energy, to do some high energy experiment in particle physics, why should we why should we accelerate them in a circular path? Why not linear accelerator? I think these things are a subject of nuclear physics and particle physics, but I just can briefly mention that, you see, in case of linear acceleration, the power loss would be very small. but still we prefer circular accelerator. If you look at the accelerator which is located at CERN, that's a I think that is a few kilometer of radius, and this is again it's a circular motion, so the particles will lose energy. So I can discuss this. I think because I will deviate from the topic which I am discussing right now, so I am not going into that. But linear accelerator, of course, the power loss will be very small. But designing a linear accelerator is, of course, very costly. And to achieve that kind of energy which we desire to have for the kind of experiment required in particle physics will be very large. So circular accelerator here you can confine that in a smaller, not smaller, but in a limited space where the particles can be accelerated. They will of course lose energy, but you have an idea how much energy will be lost during the accelerations, and you can choose your particle depending on your purpose or goal, because this formula is telling you it depends on the q to the power 4. You can have different magnetic field. So the kind of magnetic field used in CERN is I think 1 Tesla or something like that. Order of 1 Tesla is a very large magnetic field. 10 to the power 4 Gauss. Earth has a magnetic field of around a half Gauss. So you can imagine it's a very strong magnetic field. So by changing the magnetic field, you can control the power loss from the point charge. Okay. So suppose if I provide you a circular path of say 100 meter, the radius is 100 meter. This is just suppose an accelerator where the particle is gyrating in a circular path, and the energy of the particle is say 10 GeV. Suppose it is given energy is 10 GeV, 10 GeV, right? So of course this will be relativistic. Then we cannot use this formula. We have to go to the relativistic formula, which is the Leonard formula. Okay, so what is the Leonard formula? In that case, what should be the modifications? First of all, if I tell you the energy of the particle, you can straight away calculate the Lorentz factor, because E equal to what? E equal to m gamma c square. This is the total energy. So gamma is simply E by mc square. So you can, if you know the mass of the particle, you can calculate what is the gamma factor, Lorentz factor. And once you know the Lorentz factor, you can calculate the power radiated. Because in Leonard formula, when the velocity and acceleration they are orthogonal to each other, we can calculate the power by using this formula. Leonard formula, the version of Leonard formula which is used for this case is twice q square a square by 3 c cube into what? Gamma to the power 6 or gamma to the
Four.
power 4?
Four.
Right, correct. Gamma to the power 4. Gamma to the power 6 is for parallel motion, right? Gamma to the power 4. So you see, once you calculate gamma, you can use this gamma factor here. Of course, there's the acceleration, so you have to combine them together if you want, because a is given by q vb by m. This is acceleration, q vb by m. But right now this is relativistic, so you have to put the relativistic mass, not this one, right? So what should I write here? I should write q square equal to q square by 6 pi epsilon 0 cq, and I am writing a square. What is a? Q vb by not m gamma, relativistic, right, into square into gamma to the power 4, right? So there is a gamma square factor in the denominator and gamma to the power 4 in the numerator, so it will be proportional to gamma square. So if you simplify this, you can write this in terms of beta. So simplified formula will look like this. You can easily simplify this: q to the power 4 and so on, q to the power 4 beta square gamma square, because gamma to the power 4 and gamma square. So we have a gamma square here, gamma square b square, magnitude of amplitude of the magnetic field, divided by 6 pi epsilon 0 m square into c, right? So we have the desired formula for power radiated in case of relativistic motion in a circular path. So this if you so based on a problem, you have to calculate the acceleration. In this problem, we have a circular motion of a point charge around a constant magnetic field B. So in this case, the power radiated by the accelerated point charge will be given by this expression. So you see, this will be amplified by I think gamma square. This was I think q to the power 4 beta square there will be a bit of different, but again gamma square, so this will be the power loss will be much more than the non-relativistic case. And if I ask you to calculate the total energy radiated by the electron in this one, say what is the time, I mean if I ask you what is the total energy lost by the electron or say the charged particle during this one orbit, I mean one circular revolution. So if the charged particle goes from here to come back here again in a circular path, then you have to calculate the total energy lost by the particle during that time interval. Again, you can calculate the time interval. What is that time interval? In this case, delta t, or t will be how much? T will be given by twice pi r by v. How do you get v? V can be calculated from gamma, because you have calculated gamma by dividing energy, total energy, which is 10 GeV in this case, by mc square. You get gamma. From gamma you can calculate beta, and beta will tell you what is the velocity. So you divide this the entire path, the perimeter of the circle, which is 2 pi r, divide it by velocity, you get time, and you multiply the power with this time to get the total energy radiated by the charged particle during that one circular revolution. If I say what will the energy lost, say for 5 circular revolutions, just multiply by 5, right? So once you know the time, you can calculate the total energy lost from by the moving point charge. Okay, so what I have discussed today is mostly the application of the formula that we have derived, because those formula are very important in nuclear physics, particle physics, or high energy physics, right? So you should be able to use this formula in different physical situations. Okay, you have learned how to derive them, but that is not sufficient. And based on a physical condition, you have to decide which formula to use, relativistic or Leonard formula or Larmor formula, or if the velocity and acceleration are parallel, then which this formula or that formula, that you have to decide. So this is all about application, and I just told you this, don't forget the names: cyclotron radiation and synchrotron radiation. And also in the non-relativistic case, it is called the Bremsstrahlung radiation. It's a, I think, German name. Bremsstrahlung means breaking radiation. So that radiation, I think, one example is X-ray that I told in the last class, that when the electrons or charged particles are deaccelerated, in X-ray what you do, you have a very high energy electron which falls on a tungsten or something like that, a target where they get deaccelerated, and while deaccelerating, they actually radiate energy, which is nothing but this X-ray that we produce, right? X-ray is basically power radiated by these deaccelerating charged particles or electrons. One more thing which I would like to, I don't know how much time we have, let us see. I don't think we have sufficient time, but another thing which I had an intention to touch upon is that see, mathematically you have derived this formula for power radiated by the charged particle. I think we can. So I just wanted to give an idea. I mean, why the charged particles? What is the physical intuition or physical region? I mean, how do we visualize? Okay, why the charged particles should produce radiation, right? Because see, we have calculated the electric field and magnetic field for an accelerating point charge, and we have seen that electric field and magnetic field, they are orthogonal to each other, right? And just because of this orthogonality, you see this, they are orthogonal. Suppose I have a point charge here, so I'm not going to discuss this in detail, but at least I want to touch this. Suppose there is a point charge here, right? Now electric field or the say electric field is given by basically magnetic field will only arise when the charged particle starts moving, right? If it is at rest, we have already discussed about this. Magnetic field purely arises just due to special relativity, right? Unless there is a motion, you will not see magnetic field. And electric field, magnetic field are nothing but different components of the field strength tensor, electromagnetic field tensor, right? So electric field, how do we visualize that? So imagine if there is a isolated, say, one single point charge, the lines of forces. I mean, this is one beautiful concept given by Michael Faraday. I mean, who gave this concept of lines of forces, right? They're radially coming out from the charge and going to infinity. These are the electric lines of forces, and they basically give you the direction of electric field, right? And we measure the strength of the electric field by measuring the how many lines of forces are passing through a given area, or say unit area. That gives you the strength of the electric field. And now you see the electric fields are radial here, right? Radial. And there is no magnetic field, of course, so there is no radiation. Now as soon as this charged particle starts moving, we have radiation, right? Now we of course can explain why that magnetic field is originated, but in terms of this physical picture where we have these lines of forces, how do we interpret the radiation coming out of that? Maybe I can discuss this if we have some classes once we finish this core topics which are there in the syllabus, because these radial fields, they actually turn into non-radial one, and that is the reason why we have this orthogonal electric field, and then we have magnetic field which produces this non-zero Poynting vector, which you see in case of accelerated point charge. And one can actually visualize this, that why they, and we shall get actually the exact formula without much calculation, just from the some simple pictures. And that is beautiful in the sense that it gives us some insight into the problem. Because Faraday, actually, if you read the history of science, Faraday was not very proficient in mathematics, because he had no formal education. He was definitely a genius, but he had no formal education. He had no training on mathematics. So, but he had a very, uh, different kind of imagination, which he applied into different problems to figure out very difficult problems of that time. Maxwell, if you read carefully Maxwell's writings, you will find that Maxwell is a great reference for Faraday. I think what he said, that he was only able to synthesize these four law into a self-consistent form, which we call today Maxwell's equation, only because of Faraday, right? So these lines of forces, which are usually taught in school textbook, are actually very powerful things to visualize different problems and understand their inner physical meanings. So maybe I think I can discuss about this physical mechanism to give some kind of explanation which can explain at least why the charged particles radiate suddenly when it starts accelerating. But from a mathematical point of view, I think we have covered enough where we can show that since there is a radial orthogonal electric and magnetic field, not radial, electric field and magnetic field are orthogonal, and we have some field which you call acceleration field, which for which the Poynting vector falls off as 1 by r square, and because of that, and the total energy radiated will be always fine. The power radiated will be always finite, because when you multiply by the 4 pi r square, this r square terms cancels out, and if you have a, I think if you have a point charge accelerating, you will always have some kind of non-zero radiation coming out of that particle even at infinity. So I stop here, because the goal of today's class was to just give you some idea about application of this formula, which we have learned in the last few classes. If you have some questions, we can discuss. আচ্ছা, তোমরা কি তোমাদের টিউটোরিয়াল ডেটটা ফিক্স করেছো? কিছু আলোচনা করেছো তোমাদের এর মধ্যে? তোমাদের টিউটোরিয়াল কবে দেবে? আমি বলেছিলাম 15 থেকে 20-র মধ্যে হলে ভালো হয়, কারণ খাতাগুলো থেকে জমা দিতে হবে, তো তোমাদের মাস্টার পাঠাতে হবে। তোমাদের মোস্ট লাইকলি থার্ড উইক বলেছে, মানে 21st পরে হয়তো ক্লাস হবে না আর, ম্যাক্সিমাম 22, 23 হয়তো, জানি না কবে কি। তো তোমাদের একটা বলেছিলাম ডেট ফিক্স করে আমাকে জানাতে। Have you decided any date? Yes, no, or should I declare it?
বলছি যে মানে 20
I
তারিখে যাবে?
20 তারিখ। হ্যাঁ, তোমরা 20 তারিখ ঠিক আছে, তোমরা যদি সবাই এগ্রি করো, মানে আমার কাছে তোমাদের সবার এগ্রি করাটা বেশি ইম্পর্টেন্ট। 19 তারিখ 20 তারিখ যে আমার কোনো আপত্তি নেই। তো তাহলে 20 তারিখ কিবার পড়ছে?
আমি স্যার চেক করছি।
হ্যাঁ,
So Wednesday.
আচ্ছা ওয়েডনেসডে। আচ্ছা, তার আগে আমরা কটা ক্লাস পাবো বলো তো? আজকে কি, আজকে আচ্ছা ওয়েডনেসডে বললে মানে নেক্সট উইক ওয়েডনেসডে, তাই তো? তার মানে ঠিক আছে, তাহলে আমি সিলেবাস আজ আজ পর্যন্ত যা পড়ানো হয়েছে সেটাই থাক। আমি এরপরে যেগুলো পড়াবো সেটা পরীক্ষার মধ্যে রাখছি না, ঠিক আছে? মানে এই যা আলোচনা করলাম, সিঙ্ক্রোটন রেডিয়েশন, সাইক্লোট্রন রেডিয়েশন, লার্মার ফর্মুলা, লেনার্ড ফর্মুলা, এখানে পর্যন্তই পরীক্ষাটা হবে। হ্যাঁ, এরপরে আমরা যেগুলো আলোচনা করব সেগুলো আমাদের টিউটোরিয়ালে থাকবে না, সেগুলো সিলেবাসের মধ্যে থাকবে ডেফিনেটলি, মানে আমাদের কোর্সের মধ্যে, বাট টিউটোরিয়ালের মধ্যে রাখছি না। টিউটোরিয়াল আজ পর্যন্ত যা পড়ানো হয়েছে, ঠিক আছে? তাহলে ঠিক আছে তোমাদের, তাহলে আমার কালকে আবার ক্লাস আছে, সো উই শ্যাল মিট অ্যাগেন টুমরো।
Okay.